Alright guys, we're going to go over section 6 today and using the law of conservation of energy. And if we remember, the conservation of energy means all the energy I have final is going to equal all the energy I have initial if we're in an isolated system. If we're not in an isolated system, we have to do energy initial plus work equals our final energy. So that's what we're going to look at here. So what this is showing is how my kinetic, potential, spring potential, thermal will all equal the work added into it. So here all my final energy is going to equal all my kinetic. If I add work in, I may gain some thermal energy as well. So again, if we are in an isolated system, meaning no work is added to it, so our work is 0, means all my final is going to equal all my kinetic. Now, I may gain thermal energy still, and where that energy transfer would be typically is out of your kinetic. It's going to slow down whatever's moving. So this just shows how we isolated a system. Here, the earth and the ball are isolated together, so we can just look at the force and the work done on each. This box sliding down a ramp, or the spring, even an object sliding along, they're all isolated systems because we are not adding any work to the system. So if we look, a spring-loaded toy gun shoots a plastic ball with a launch speed of 2 meters per second. So if the spring is compressed twice as far, the ball's launch speed will be what? Well, what we need to look at for our change in speed is going to be the amount of work added to it. So if we look here in our conservation of energy, my kinetic energy is going to change by the amount of spring energy added. Okay, so if my change in x, this number doubles here because it's squared, my velocity is going to double because it's squared as well. The mass didn't change, so by changing, my distance moved is going to change the velocity. So if we start with 2 meters per second, doubling the change in the spring will double my velocity. If I go back to this one, now we're changing this k value, and we're going to ask how our velocity changes. So right away I notice this value, this k value, is not squared, but my velocity is. So I'm probably not going to have a direct correlation like I did in this problem. It's going to be a correlation of a square. Alright, so now we're replacing that spring with a new spring, having twice the spring constant. Now changing the spring constant, but keeping the distance the same, is going to also change the launch speed. Because we changed that k, so look at this. With my conservation of energy, if I double k, my velocity is going to increase by the square root of 2. So my 2 meters per second goes to 2.8 meters per second. Instead of doubling it, you multiply it by the square root of 2. A lot of those problems, it's easier if you just plug numbers in and look at it that way. But if you look at the variables, you could figure it out as well. So one equation that we can look at and will help with this, we have an isolated system with this car. It sits at rest at the top of a hill. A small push, so small that our work is 0. So we're not adding any work to it. So my conservation of energy remains here. So when I look at this, what I can say is that as this car starts rolling down the hill, it drops by 5 meters. So my change in energy is gravitational potential by 5 meters. So my potential initial is going to equal my kinetic final. Now, I have no kinetic initially. The car sits at rest to start. And we're going to say as it goes down the hill, the 5 meters, the potential is going to go to zero, the final potential energy. So that's why in this equation, all I have is initial potential and final kinetic, because I have no initial kinetic, starts at rest, and I have no final potential energy because we're going to say it's at zero. The drop went to zero. So looking at this equation for potential, mg, how high it is going to be 1/2 mass velocity squared. Now you might be saying, they never give me the mass of this car. Well, it does not matter. I can divide mass out of both sides of this equation. So if we are solving for velocity, and this is an equation in an isolated system that we're going to look at quite a bit, what we can do is solve for velocity here. So if I double both sides, gets rid of my half. Now take the square root. My velocity is equal to the square root of 2 times 9.81 times, in this case, 5 meters. So my velocity in this case is going to end up being 13 meters per second. And that'll be the velocity of this car at the end when it drops the 5 meters down the hill. So this equation is one that you may want to note, that velocity equals the square root of 2 times acceleration due to gravity times y. This equation right here. That is one anytime in an isolated system that you can use. Now if we add work to it, we can't use that equation. Alright, so here a child slides down a slide at a constant speed of 1.5 meters per second. It says the height of the slide is 3 meters. Write down the equation for the conservation of energy, noting the choice of system, the initial and final states, and what energy transformation has taken place. So as this child goes down the slide, there's a constant speed. So my initial kinetic and final kinetic doesn't change. But we are getting a change, however, in potential energy because it dropped 3 meters. So when this happened, where did that change of energy go? So if I look at my energy initial having to equal my energy final, in this case it seems to be adding energy because or losing energy because my initial potential had 3 meters. We can kind of think of this as dividing both sides by kinetic energy. So my initial energy, I have potential, gravitational initial, plus kinetic initial, should equal potential final plus kinetic final. Now the problem with this is there's a constant speed. So my kinetic initial, my kinetic final go away. But I can have an initial potential equal my final potential because it dropped 3 meters. So the other thing that you're gaining here is thermal energy. As this child slides down the slide, they are going to gain thermal energy. So now, as the potential energy initial drops, okay, so this number of potential initial is going to drop when it goes to potential final. Well, the transfer goes to thermal energy. So in this case, we take into account the 3 meter drop is converting some energy to thermal energy. So take note of those systems. How they can remain at a constant speed is because energy is being transferred to thermal energy. Alright, so at the county fair, Katie tries the water slide. The shape is shown, so it looks like this. Starting 9 meters above the ground, she pushes off with an initial speed of 2 meters per second. Slide is frictionless, so unlike the last problem, we don't have to worry about thermal energy. We want to know how fast is she going afterwards in this case. So we can think back to the problem we did before in solving for that final velocity. We have an isolated system, so we can come back to this equation. The final velocity is going to equal the square root of 2 times acceleration due to gravity times y. So when I put into here 9.81 and I put into here the drop of 9 meters, when I solve this, I'm going to get about 13 meters per second. What does it is they're going to bring you through all of the energies. So all my final equals all my initial. So they change this. Again, we can get rid of mass. It would delete out of every part of this equation. But eventually what we're going to see is that same equation. Now the only difference, okay, and I forgot to put it before, the only difference is we have to keep that initial velocity. We have to add that to it. So when we do our 9 times 2 times 9.8, we have to add to it that initial velocity, and it's initial velocity squared because that's how we have it in this problem. So don't forget in this problem to add, in this case, that initial velocity. I forgot to write that on the previous slide, but this is key. Don't forget, because she initially was starting at 2 meters per second, we have to add that in. Okay, so all they did here is they solved for this variable to go to here, and then they plugged the numbers in to get our 13 meters per second. Alright, so on this one, Monica pulls her daughter Jessie in a bike trailer. They together have a mass of 25 kilograms. They start up a 100-meter long slope, 4 meters high. She applies a constant force of 8 newtons. So they start out at the bottom of the slope with a speed of 5.3 meters per second. So again, we have an initial velocity here. What is their speed at the top of the slope? So as they go up the slope, we want to know what that is. So here's a representation of that. Start at the bottom, finish at the top. What do we know? Initially, their y value, or how high they up, is 0, which tells us I start with an initial potential energy of 0. But I have initial kinetic energy because 25 kilograms is moving 5.3 meters per second. Now, it seems that we would gain energy by doing this, by still moving but going up the hill. So our final velocity may go down, but there's something else being added here, and what's being added is work. And if we remember, our equation for work is force times distance, and they give us both of those. So I'm going to have to add in to my equation how much work is put in. So the initial energy plus work will give me my final, and that's what we're going to show here. So that initial energy, kinetic, okay, this potential is 0 because it started at 0. We're going to say there's no friction, so we don't have to worry about thermal energy. So my initial kinetic plus work is going to equal my final kinetic plus final gravitational potential energy. Now, they are going to keep the initial here, but know that this y value is 0, so you essentially can get rid of that term. Okay, is come back to this equation and substitute instead of work. Remember, work is force times distance. So we're going to do 1/2 mass initial velocity squared plus work being force times distance. Most of you probably prefer to do it this way and then put in your variables into each one of these terms of this equation and then solve. So they go ahead and solve for the final velocity equation. What you may want, the book is going to solve for final velocity, put in the values, and solve. Our final velocity is 13.7 meters squared per second squared, because that's velocity final squared. Once we take the square root of that, we get 3.7 meters per second. So initially she was moving 5.3 meters per second. She slowed to 3.7. So we lost some kinetic energy there, but we gained potential. And we actually gained more potential than what we lost kinetic. And the reason that we can do that is because work was put in. So we still conserved energy, but we put energy in. So we put more energy in by doing work, pedaling up the hill, so we can get more final energy. All right, so this is just showing the kinetic gravitational potential, elastic potential. This is just showing us these different equations. So a couple of slides here are just showing us these equations. Now, if we wanted to solve for our thermal energy, remember that's friction force plus how far it, or times, sorry, how far it slides. And again, in an isolated system, the law of conservation of energy tells us that our final total energy equals our initial total energy. If they don't equal each other, okay, it's because work was added. And if work is added, we have to add that to our initial here. But when work is added, we then are not in, it is still a law of conservation of energy, but it is not an isolated system anymore. Okay? So, law of conservation of energy, all of our initial energy will equal all of our total energy. All right, so if you guys will go ahead, work on your homework problems. I will be back Monday. Any questions on this I can go through. I'm thinking there's 2 more sections to this chapter, so we're probably going to have a test later next week, Wednesday, Thursday, Friday-ish. Probably thinking closer Thursday, Friday-ish. So go ahead and get to work on your homework and be caught up, get through section 6. All right, guys, have a good day, have a good weekend.